Mars is not just a red planet. It's a frozen world of extreme mysteries. It has the largest volcano in the solar system, rising nearly 3 times taller than Mount Everest. It has a canyon system so massive it stretches thousands of kilometers, deeper than anything on Earth. And it has dust storms so powerful they can engulf the entire planet for weeks, sometimes months. But the strangest part is this: Mars wasn't always like this. Long ago, this planet may have had rivers, lakes, and possibly even an ocean. Scientists have found minerals that only form in water, and evidence of ice buried just beneath the surface. So what happened? How did a world that may have once been habitable become a cold desert with an atmosphere so thin it can barely protect anything alive? To uncover the truth, we must explore Mars' landscapes, its climate, and the violent history written into its surface, because Mars may hold the biggest answer of all. Are we truly alone in the universe? To begin answering that question, we must first explore Mars itself. We must begin with its surface, its volcanoes, craters, and ancient landscapes carved by time. Olympus Mons is the tallest planetary volcano, towering 22 kilometers high, formed by long-lived lava flows on a stagnant crust. Its massive shield shape rises so gradually that an observer standing on its lower slopes might not realize they are climbing a giant at all. The volcano's base spans nearly 600 kilometers, wide enough to cover an entire country, revealing how countless eruptions built it layer by layer over millions of years. This immense scale makes Olympus Mons one of the most extraordinary volcanic structures in the solar system. Olympus Mons is so vast that its base could span the entire state of Arizona. Rising 22 kilometers high, nearly 3 times the height of Mount Everest, it dominates the surrounding plains of Mars. Its shallow slopes, averaging only 5 degrees, formed from countless, slow-moving lava flows that built this shield volcano layer by layer over hundreds of millions of years. Its massive footprint and gentle profile reveal that Mars once possessed long-lived volcanic hotspots similar to those, though far stronger, than those forming the Hawaiian Islands on Earth. Unlike Earth, Mars has no mobile tectonic plates. Instead, a single stationary crustal plate allowed Olympus Mons' volcanic hotspot to erupt repeatedly in the same location for eons. This stability enabled lava to build upward to extraordinary heights. Many lava flows stretch over 500 kilometers across the Tharsis region, freezing into vast plains of basalt. Evidence suggests that eruptions may have continued into Mars' relatively recent past, possibly just a few tens of millions of years ago, making Olympus Mons one of the youngest major volcanoes in the solar system. At its summit lies a spectacular 85-kilometer-wide caldera complex, formed through repeated collapses after major eruptions emptied the magma chambers below. These calderas reveal the volcano's explosive history, each collapse marking the end of a massive eruptive phase. Surface mineral studies show altered volcanic materials that once interacted with heat, gas, and possibly subsurface ice, hinting at hydrothermal systems that could have created habitable environments deep underground. Because Olympus Mons rises into the thin upper atmosphere, clouds often form around its summit, creating a halo visible from orbit. At its base, ancient lava channels and ash deposits tell the story of a once active volcanic landscape. Some models suggest that the volcano's immense mass may have influenced regional gravity and even contributed to the formation of nearby canyons and faults within the Tharsis region. Today it stands dormant, a colossal monument to Mars' fiery past and a key to understanding how the planet evolved geologically. The Tharsis Bulge is a colossal volcanic plateau on Mars, spanning nearly 5,000 kilometers, roughly the width of the entire United States. This raised region is home to the largest volcanoes in the solar system, including Olympus Mons and the aligned Tharsis Montes. Scientists believe it formed from an enormous plume of hot rock rising from deep inside Mars. Over billions of years, this upwelling reshaped the crust, created massive fractures, and may have altered the planet's climate by tilting its axis. Tharsis is one of the most influential geological structures in Mars history, a volcanic dome so massive that it changed the planet's rotation and gravity field. The immense weight of its volcanoes caused the crust to crack thousands of kilometers away, forming Valles Marineris, the largest canyon system in the solar system. Tharsis also released enormous amounts of volcanic gases into the atmosphere, which may have warmed early Mars enough for liquid water to flow across its surface. The Tharsis Bulge rose from repeated volcanic eruptions that lasted hundreds of millions of years, building a plateau up to 10 kilometers high. Beneath its surface lies a complex network of ancient magma reservoirs that once fed eruptions across the region. The alignment of the giant Tharsis volcanoes, Olympus Mons, Volcanoes Mons, and Valles Mons, suggests a long-lived hotspot fixed beneath the crust. These volcanic forces sculpted the Martian landscape on a scale unmatched anywhere else in our solar system. Seen from orbit, the Tharsis Bulge appears as an enormous swell on the Martian globe, a volcanic plateau covering nearly a quarter of the planet. Its formation released enough lava to blanket entire continents. The weight of this immense structure forced the crust to bend and stretch, creating global-scale tectonic features. Scientists think the Tharsis region may have once generated thick clouds and long-lasting volcanic eruptions that shaped the climate of early Mars, influencing conditions for possible ancient life. Tharsis is a geological powerhouse. Its volcanoes rise to extraordinary heights due to Mars' low gravity and lack of shifting tectonic plates. Unlike Earth's moving crust, the Martian surface remained fixed over a persistent hotspot, allowing volcanoes to grow for eons. The plateau's uplift redirected ancient river systems and may have driven catastrophic floods across the lowlands. Understanding Tharsis helps scientists uncover how internal heat and volcanic activity shaped Mars' evolution from a once active world to the quiet desert planet we see today. Valles Marineris plunges as deep as 7 kilometers, so deep that if you stood on one rim, the opposite side would disappear beyond the curvature of Mars. Stretching more than 4,000 kilometers, this canyon is 10 times longer and several times deeper than Earth's Grand Canyon. But it wasn't carved by a river. Scientists believe it formed when the crust cracked and pulled apart under the immense stress of the nearby Tharsis volcanic region. Its towering walls expose billions of years of geological history preserved in layered rock. Valles Marineris is the largest canyon system in the solar system, a colossal scar created not by water, but by the stretching and fracturing of Mars' crust. Some sections descend more than 7 kilometers, exposing ancient sediments, volcanic ash layers, and minerals altered by past fluids. Landslides have shaped many of its walls, leaving behind enormous debris piles that span entire cities. The canyon's scale reveals the tremendous tectonic forces that once reshaped the Martian surface on a planetary level. Running nearly a quarter of the way around the planet, Valles Marineris is a vast interconnected system of chasms formed when Mars' crust was torn open. The nearby rise of the Tharsis Bulge pulled the surface apart, creating deep troughs that later widened through landslides and erosion. Orbital observations reveal layered deposits that may record ancient climate cycles, as well as minerals that formed in the presence of water. The canyon's depth provides a window into Mars' interior like nowhere else on the planet. Valles Marineris sinks deeper than any canyon on Earth, carved not by flowing rivers but by the structural collapse of Mars' crust. Its main chasm, Valles Chasma, reaches depths of over 7 kilometers and contains vast deposits of sulfates and other minerals formed in ancient watery environments. The canyon walls reveal hundreds of rock layers, each representing a different era of Martian history. This immense scar shows how volcanic uplift, tectonic stretching, and slow erosion shaped the planet's dramatic landscapes. Few features in the solar system rival the scale of Valles Marineris. Formed when Mars' crust fractured under the stress of rising magma beneath Tharsis, the canyon's deepest sections drop more than 7 kilometers. Over time, landslides, wind erosion, and possibly short-lived water activity widened its troughs into the massive valleys we see today. Its exposed rock layers provide an unparalleled archive of Mars' volcanic, tectonic, and environmental evolution, offering clues about a planet that once was far more dynamic than today. Hellas Basin is one of the largest impact structures in the entire solar system, spanning about 2,300 kilometers across, wide enough to fit the entire Mediterranean Sea. Formed over 4 billion years ago by the collision of a massive asteroid, the impact excavated a depression 8 kilometers deep and reshaped the surrounding terrain. The basin's great depth traps cold air, making it one of the warmest regions on Mars during the day and one of the coldest at night. Its floor contains layered sediments, dust deposits, and minerals that may record ancient climatic cycles, offering scientists clues to early Martian atmospheric conditions. Hellas Basin was born in a cataclysmic impact that released energy greater than millions of nuclear bombs combined. This enormous basin plunges deeper than Mount Everest is tall, creating a natural bowl where atmospheric pressure is higher than anywhere else on Mars, about double the planet's average. These conditions allow frost, fog, and even thin layers of seasonal ice to form along its floor. Radar observations reveal sedimentary deposits that may have been shaped by ancient glaciers or dust-laden winds, making Hellas a key site for studying Mars' shifting climate over billions of years. With a diameter stretching more than 2,000 kilometers, Hellas Basin stands as one of the most dramatic reminders of Mars' violent early history. The enormous impact that created it generated shock waves strong enough to fracture the crust far beyond the basin's rim. Its depth traps atmospheric gases and dust, giving it unique weather patterns, including some of the most frequent dust storms on the planet. Orbital imagery shows layered deposits and bright mineral patches that may contain sulfates and other water-related signatures, hinting that Hellas could preserve traces of ancient Martian environments. Hellas Basin is a geological treasure, revealing the story of Mars from its earliest days. Formed during the late heavy bombardment, this colossal depression records billions of years of erosion, impact modification, and climate evolution. Its depth creates a microenvironment with higher pressure that may have allowed liquid water to exist transiently in the past. Scientists have detected dust-rich sediments, possible glacial features, and minerals that typically form in the presence of water or ice. Studying Hellas gives researchers a unique window into Mars' atmospheric loss, surface weathering, and ancient hydrologic potential. Hellas Basin's vast interior is a natural laboratory for understanding Martian geology and climate. The impact that carved this gigantic bowl likely ejected material across half the planet, influencing surface evolution on a global scale. Today, the basin's immense depth causes air to accumulate, producing local weather systems unlike those anywhere else on Mars. Dust storms often originate here, rising from bright dust deposits that blanket the floor. High-resolution imagery reveals polygonal ground, wind-sculpted ridges, and layered sediments, all of which preserve evidence of changing temperatures, pressure, and ice cycles over Mars' long history. Meridiani Planum, a vast, rust-hued plain straddling the Martian equator, is a geologist's treasure trove and a cornerstone in the story of ancient Martian water. While Mars today is a hyper-arid desert, this region holds definitive proof of a wetter, more element past. The Opportunity rover, exploring here for years, discovered a landscape littered with peculiar, spherical concretions, small, blueberry-like beads of the mineral hematite, which typically forms in the presence of liquid water. These peppered the surface and were embedded within vast, layered sedimentary bedrock. This bedrock itself is composed of sulfate salts and fine-grained sediments, a clear signature of an ancient, shallow, and likely acidic sea or a series of evaporating playa lakes. The chemistry tells a story of water interacting with volcanic ash, precipitating minerals, and then vanishing as the planet's climate changed irrevocably. Meridiani Planum is not just a dry lake bed, it is a billion-year-old chemical archive, preserving the moment Mars began to dry out, locking the evidence of its last sustained surface waters into stone. Arabia Terra, a vast ancient region in Mars' northern hemisphere, is not defined by dramatic peaks or canyons, but by a profound, eroded subtlety. Its landscape of softly contoured mesas and buttes, glowing with golden and buff-colored hues, is a palimpsest of climatic history. These layered mounds are the eroded remnants of what was once a far more extensive blanket of sediment. likely a combination of volcanic ash, wind-blown dust, and possibly lakebed deposits, laid down billions of years ago when the atmosphere was thicker. The intricate, yardarm-like sculpting seen on their flanks is the meticulous work of eons of abrasive Martian winds, carving the once continuous layers into isolated islands. Crucially, the chemistry within these layers varies. Some show signs of alteration by slightly acidic water, while others are bone-dry. Arabia Terra thus acts as a stratified timeline, its mesa walls recording the planet's long, tortuous transition from a world capable of supporting persistent surface water to the globally arid, wind-dominated planet we see today. Spanning the vast northern lowlands of Mars, Utopia Planitia presents a landscape of seemingly endless, tranquil plains. Its most striking feature, visible from orbit, is a sprawling network of polygonal patterns etched into the surface, cracks forming shapes ranging from the size of a small room to larger than a city block. These are not random fractures, but the direct signature of a subsurface frozen layer, a process analogous to permafrost terrains on Earth. The polygons form due to the thermal contraction of ice-rich soil in the Martian regolith. As temperatures plunge dramatically during the long Martian winter, the ground contracts and cracks. Over countless annual cycles, this repeated stress builds a network of tensile fractures. This patterned ground is a powerful, visible testament to the presence of shallow ground ice, a critical resource. It reveals a landscape where the modern climate actively interacts with buried water ice, shaping the terrain through persistent, rhythmic freeze-thaw cycles in the shallow subsurface. Gale Crater is not merely an impact scar. It is one of Mars's most profound and carefully read geological manuscripts. The crater's central peak, Mount Sharp, is a towering monument of sedimentary layers, each stratum a chapter in a billion-year environmental saga. A flyover reveals its foothills as a stunning cross-section of history, where distinct bands of mineralogy tell a clear story of transformation. The lower slopes are rich in clay minerals, which form only in neutral, benign water, evidence of a long-lasting, potentially habitable lake environment in the crater's deep past. As the eye travels upward, these clays give way to bands dominated by sulfate salts. This mineralogical transition is critical. It marks a dramatic shift in the crater's chemistry, as the once persistent lake began to evaporate, becoming increasingly acidic and salty before vanishing entirely. Gale Crater therefore preserves a rare and continuous record of Mars's climate descent, from a world with enduring, fresh bodies of water to one where only bitter, ephemeral brines remained. Jezero Crater presents one of the most compelling astrobiological sites in our solar system. Its landscape bears the unmistakable fingerprint of a complex, persistent aquatic past. The visual evidence is stunning, a beautifully preserved, fan-shaped river delta, where ancient channels branch out like veins as they meet the crater wall. This is not the result of a single flood, but of a river system that flowed consistently, carrying fine-grained sediments and eroded clays from a vast watershed into a standing body of water that filled the crater basin. This calm lake environment is the key. As the river waters slowed upon entering the lake, they dropped their sedimentary cargo layer by layer, efficiently trapping and burying any organic matter or chemical traces of life that may have been carried from upstream. Jezero Crater therefore is a fossilized catchment basin, designed by geology to collect, concentrate, and preserve the very materials that could hold the first evidence of life beyond Earth. Noctis Labyrinthus is one of the most complex and mysterious regions on Mars, a sprawling maze of intersecting valleys, towering mesas, and steep-walled depressions marking the western gateway to Valles Marineris. This fractured landscape was formed billions of years ago as giant blocks of the Martian crust collapsed along deep, widening faults created by the immense tectonic stresses of the nearby Tharsis volcanic rise. As the crust stretched and thinned, vast sections sank unevenly, producing a chaotic network of troughs that reached several kilometers deep. The exposed cliff faces reveal layers of ancient rock, some altered by water-rich minerals, suggesting that groundwater once circulated through these fractured zones. Scientists believe the area may have hosted ice or even hydrothermal activity during Mars' early history. Today, in the low sunlight of the Martian dawn or dusk, the valleys glow with warm hues, emphasizing the dramatic vertical relief of this geologic labyrinth, one of the planet's most striking records of internal forces shaping its surface. As the second largest impact basin in Mars' southern hemisphere, Chrysoplanidia possesses a scale that is almost beyond terrestrial comprehension. Its formation billions of years ago created a colossal topographic depression, a natural catchment over 1,000 kilometers wide. This vast, enclosed lowland is key to its story. Today we see it as a stark, often snow-dusted plain encircled by a complex, hazy ring of eroded mountains, the battered remnants of the crater rim. This topography presented a monumental opportunity on early Mars. The prevailing scientific hypothesis suggests that during periods of higher obliquity, when the planet's tilt directed more sunlight to the poles, substantial ice deposits from the southern highlands could have melted. This meltwater would have been funneled by immense networks of valleys directly into the profound depths of Chryse. There, liberated from the thin atmosphere, it would have pooled, potentially creating a vast ice-covered lake that persisted for millennia, making Chryse not just an impact scar, but a fossilized cold climate basin that may have intermittently hosted a major body of standing water. Elysium Planitia is one of the youngest volcanic regions on Mars, a vast expanse of dark basaltic plains shaped by relatively recent geological activity. Unlike many ancient terrains elsewhere on the planet, the surface here displays fresh-looking lava flows, fissure vents, and broad volcanic fields that may be only a few million years old, geologically recent by Martian standards. Orbital imagery reveals long, branching channels carved either by flowing lava or catastrophic floods of water released from underground reservoirs. Some fissures appear to have erupted vigorously, sending molten rock across the plains and leaving behind smooth, ropey textures similar to those found in Hawaii. There is even evidence of steam-like plumes and thermal data, suggesting that Mars may have experienced volcanic or geothermal activity far more recently than once believed. Elysium Planitia offers scientists a rare glimpse into Mars' youthful, active past and raises the intriguing possibility that heat still lingers beneath its crust today. The polar dune fields of Mars are among the most striking landscapes on the planet, sweeping, dark blue to black dunes lying atop bright icy ground near the north and south poles. These dunes are composed of basaltic sand, derived from ancient volcanic rocks that have been ground into fine grains by eons of erosion. Despite Mars' thin atmosphere, winds are still strong enough during certain seasons to push these dunes across the polar plains, causing them to migrate a few meters over the course of a Martian year. High-resolution orbital images reveal intricate ripple patterns formed by repeated freeze, thaw cycles and seasonal carbon dioxide frost. In winter, the dunes become coated in a thin layer of dry ice, which sublimates in spring, triggering small avalanches and releasing jets of gas that reshape the surface. These dynamic processes make the polar dunes one of the most active geological regions on modern Mars, offering scientists a rare glimpse into how wind, ice, and seasonal sunlight continually sculpt the Martian surface. Medusae Fossae is one of the most enigmatic formations on Mars, an immense deposit of soft, easily eroded material stretching for nearly 1,000 kilometers along the planet's equator. Unlike most Martian landscapes carved by impacts or volcanoes, this region appears to be composed of fine, lightweight sediments that have been shaped over millions of years by relentless winds. Scientists believe the deposit may have formed from enormous volcanic eruptions in the nearby Tharsis region, releasing ash and pyroclastic flows that blanketed the surface in thick layers. These layers have since been sculpted into smooth hills, sharp ridges, and isolated mounds with textures unlike any other terrain on Mars. Radar measurements reveal low density, suggesting that Medusae Fossae is far more porous than typical rock. Its fragile structure is constantly reshaped by wind erosion, making it one of the most rapidly changing landscapes on the planet today. Understanding this mysterious deposit offers valuable clues about Mars' volcanic past and the powerful atmospheric forces that continue to shape its surface. Amazonas Planitia is one of the youngest and smoothest volcanic plains on Mars, a vast region shaped by extremely fluid lava flows that once spread across the surface like a dark ocean. Unlike older, heavily cratered terrains, Amazonas displays remarkably few impact scars, suggesting that much of its surface formed in the recent geological past, perhaps only a few hundred million years ago. Its smoothness comes from repeated episodes of low-viscosity lava resurfacing the plains, erasing older features and leaving behind large expanses of nearly level ground. The region also contains mysterious surface textures known as etched terrains and sinuous channels that may trace the paths of ancient lava rivers. Some features resemble terrestrial flood basalts, indicating enormous eruptions capable of covering hundreds of thousands of square kilometers. Because Amazonas planitia preserves some of Mars' most recent volcanic activity, it plays a crucial role in helping scientists understand how long the planet remained geologically active and how internal heat shaped its evolution long after its early history. But Mars is more than rock and landscape. To truly understand this planet, we must look upward, into its thin atmosphere, its brutal weather, and the storms that continue to reshape the surface even today. Mars' atmosphere is extremely thin, less than 1% the density of Earth's, and composed primarily of carbon dioxide, with smaller amounts of nitrogen, argon, and trace gases that help scientists trace atmospheric processes over time. This thin air provides almost no shielding from harmful radiation and allows heat to escape rapidly, causing surface temperatures to swing by more than 100 degrees between day and night. Despite these limitations, the Martian atmosphere remains surprisingly active. Seasonal winds sweep across the planet, sculpting dunes, lifting dust, and creating haze that can linger for days. Wispy water ice clouds drift over the great volcanoes, while in winter, carbon dioxide freezes directly out of the air to build immense seasonal polar caps. These changes reveal an atmosphere that, although delicate, still interacts constantly with the surface. By studying its chemistry, circulation patterns, and seasonal cycles, scientists can piece together how Mars evolved from a thicker, warmer atmosphere in the distant past to the cold, tenuous envelope we see today. Global dust storms on Mars are among the most powerful and dramatic weather events in the entire solar system. Roughly every few Martian years, small local storms begin to grow, feeding on sunlight and rising warm air until they expand and merge into a single planet-encircling system. These storms lift billions of tons of fine powdery dust high into the atmosphere, particles so tiny that they can remain suspended for weeks. As the dust spreads, daylight dims, the sky turns a deep orange and surface temperatures drop sharply while the upper atmosphere heats dramatically, redistributing energy across the planet. During these events, familiar surface features, impact craters, canyon systems, and even massive volcanoes, fade from view beneath a swirling, opaque veil of dust. Spacecraft observations show how these storms reshape atmospheric circulation, drive global winds, and influence long-term climate patterns. They may even accelerate the slow loss of atmospheric gases into space. The sheer scale and intensity of global dust storms reveal that despite its thin air, Mars is still a world driven by powerful, ever-changing forces. Local dust devils are some of the most dynamic weather phenomena on Mars, forming when sunlight heats the surface and causes warm air to rise rapidly through pockets of cooler air above it. This temperature contrast creates spinning columns of wind that can stretch hundreds of meters high. Though smaller than the massive dust storms that sweep the planet, dust devils play an important role in the Martian environment. They lift fine particles into the atmosphere, shaping dune fields and contributing to the planet's persistent haze. Their paths leave behind dark streaks where surface dust has been removed, providing scientists with a natural record of their movement. Remarkably, these vortices have even helped clean the solar panels of rovers like Spirit and Opportunity, extending their missions far beyond expectations. Studying Martian dust devils helps researchers understand boundary layer weather, surface heating, and the delicate interactions between Mars' thin atmosphere and its dusty landscape. Each Martian dawn brings a transformation across the landscape as delicate layers of frost begin to glow in the first light of day. Unlike Earth, much of this frost is made not of water ice, but of carbon dioxide that has frozen out of the thin atmosphere during the frigid Martian night. Temperatures often fall low enough for CO2 to condense directly onto rocks, dunes, and dust, forming bright, reflective patches that blanket the ground for only a few hours. As the sun rises higher, this frost sublimates, turning straight from solid to gas, sending faint wisps of vapor drifting into the cold morning air. High-resolution images show how this daily cycle etches patterns into the soil, subtly reshaping slopes and revealing fine textures on the surface. In some regions, repeating frost cycles create alternating light and dark bands that mark seasonal changes, almost like natural climate signatures. These fleeting frosts offer scientists valuable insights into heat flow, day-night temperature swings, and how Mars' unique atmospheric chemistry interacts with its diverse terrain, revealing a planet still active in subtle but measurable ways. Nighttime on Mars transforms the planet into one of the coldest environments in the solar system. Because the atmosphere is less than 1% the thickness of Earth's, it cannot trap the heat absorbed during the day. As the sun sets, warmth escapes rapidly into space, and temperatures can plunge below -100 degrees Celsius, even in regions that were comfortable by Martian standards only hours earlier. The ground cools first, radiating heat outward, while the thin air above it loses energy almost instantly, creating steep temperature gradients across the landscape. Thermal instruments aboard orbiters reveal this transition vividly. The surface shifts from warm oranges and reds into deep blues and purples as each type of terrain cools at a different rate. Rocky outcrops, sandy plains, and patches of buried ice all radiate heat differently, producing a mosaic of nighttime temperatures. In some areas, frost forms overnight and then vanishes with the return of morning light. Understanding these extreme daily cycles helps engineers design equipment that can survive the cold and gives scientists insight into heat flow, atmospheric behavior, and how dramatically conditions on Mars can change from day. Mars undergoes one of the most dramatic seasonal transformations in the solar system as its polar caps grow and shrink each year. Unlike Earth, where the poles are dominated by water ice, Mars' seasonal caps are made largely of carbon dioxide that freezes directly out of the atmosphere during the long, frigid winter months. As temperatures plunge below -120 degrees Celsius, CO2 gas turns into frost and solid ice, expanding the polar caps until they stretch for hundreds of kilometers across the Martian surface. With the return of sunlight in spring and summer, this frozen carbon dioxide begins to sublimate, turning straight from solid to gas, and re-enters the atmosphere, causing the caps to retreat just as quickly as they formed. Orbiters have captured this cycle in striking detail, showing bright winter frost spreading over dunes, crater walls, and plains before disappearing again with the change of season. The waxing and waning of these carbon dioxide caps not only reshape the landscape temporarily but also drive powerful atmospheric currents, influencing winds, pressure patterns, and the overall climate system of Mars. Water ice clouds on Mars form some of the planet's most delicate and beautiful atmospheric features. Unlike Earth's thick, moisture-rich clouds, these Martian clouds are made from tiny crystals of frozen water suspended in an atmosphere far too thin to hold much vapor. They often appear at high altitudes, drifting across the sky in bright, wispy formations. One of the most striking examples occurs above Mars' giant volcanoes, where moist air is forced upward along towering slopes. As it rises, the air cools rapidly, allowing water vapor to condense into long, feather-like plumes that can stretch for hundreds of kilometers. These clouds change shape throughout the day, lengthening in the morning, dispersing by afternoon, and sometimes reforming in the evening as temperatures fall. Observations from orbit show these clouds tracking seasonal patterns, becoming most prominent when sunlight warms buried ice and releases small amounts of moisture into the atmosphere. By studying their altitude, movement, and composition, scientists gain insight into the daily weather cycle on Mars, the properties of its thin air, and the subtle processes that still transport water across the planet's sky. One of the most important discoveries about Mars is that it is slowly losing its atmosphere to space. Because the planet lacks a global magnetic field, the upper atmosphere stands exposed to the solar wind, a constant stream of charged particles flowing outward from the sun. When these energetic particles collide with atoms high above Mars, they can knock them loose, sending oxygen, carbon, and hydrogen drifting into space. This process, known as atmospheric escape, has been occurring for billions of years and is one of the primary reasons Mars transformed from a once warmer, wetter world into the cold desert we see today. NASA's MAVEN mission has measured this loss directly, watching as solar storms intensify the stripping effect, sometimes increasing escape rates by a factor of 10. MAVEN's observations reveal how different gases leave the planet, how solar radiation breaks apart molecules, and how Mars' thin atmosphere continues to evolve. By understanding atmospheric escape, scientists can reconstruct the planet's ancient climate and learn how long liquid water may have persisted on its surface, key clues in the search for past habitability. Martian sunsets are among the most striking sights in the solar system, bathing the horizon in a cool blue glow rather than the warm reds we see on Earth. This unusual color comes from the fine, powdery dust suspended in Mars' thin atmosphere. These dust grains are just the right size to scatter red light outward, away from the direction of the sun, while allowing blue light to pass more directly through the haze. As the sun sinks below the horizon, its rays travel through a longer path of dusty air, enhancing this selective scattering and causing the sky around the sun to turn a deep, almost icy blue. Because the atmosphere is so thin, the transition from daylight to twilight is rapid, and the glowing blue halo appears only briefly before fading into darkness. Rovers on the surface have captured these moments, showing delicate wisps of dust illuminated by the last traces of sunlight. Subtle changes in the shade and intensity of the blue glow reveal variations in dust concentration and particle size. By studying Martian sunsets, scientists gain valuable insight into atmospheric structure, dust dynamics, and how even a tenuous atmosphere can dramatically shape the way light behaves on another world. Seasonal dust waves are one of the defining features of Martian weather, sweeping across vast plains as sunlight warms the surface and stirs the thin atmosphere into motion. During the warmer seasons, the upper layers of dust loosen from the ground and become easily lifted by winds that develop as temperature differences grow between day and night. These pulses of activity can begin as small, localized gusts but quickly expand into rolling fronts that travel for hundreds of kilometers, carrying fine particles high above the surface. Time-lapse images from orbit show these dust waves brightening and dimming as they move, revealing shifting patterns of airborne sediment shaped by Mars' rapidly changing winds and low atmospheric density. As the waves pass, they can temporarily obscure craters, dunes, and valleys beneath a soft, drifting haze. Seasonal dust activity plays a crucial role in controlling the planet's energy balance, reflecting sunlight back into space while simultaneously warming the atmosphere by absorbing heat. Over time, these processes influence wind circulation, surface erosion, and the evolution of larger storms. By studying how dust waves form, migrate, and fade, scientists gain critical insight into Martian climate dynamics and the mechanisms that sometimes escalate local disturbances into planet-wide dust events. Carbon dioxide snowfall is one of the most unusual weather phenomena on Mars, occurring only near the poles during the coldest periods of winter. As temperatures plunge below -125°C, carbon dioxide in the atmosphere freezes directly into tiny ice crystals, forming clouds that release faint, whisper-like snow. Unlike water snow on Earth, CO2 snowflakes are extremely small, often no larger than dust particles, and fall slowly through the thin Martian air, creating a soft shimmer rather than a visible shower. The polar night, illuminated only by starlight and faint atmospheric glow, is when this snowfall is most active. Orbiters equipped with infrared instruments have detected these CO2 clouds from above, while landers have recorded temperature drops consistent with surface frost accumulating overnight. The seasonal buildup of CO2 snow contributes to the growth of Mars' winter polar caps and plays an important role in controlling atmospheric pressure. When spring arrives, this frozen carbon dioxide sublimates rapidly, re-entering the atmosphere and driving strong winds and regional weather shifts. Studying CO2 snowfall helps scientists understand the planet's extreme climate cycles and the delicate balance between atmosphere, ice, and temperature. The InSight lander provided one of the most detailed views ever recorded of daily Martian weather, using a suite of highly sensitive instruments designed to measure wind, atmospheric pressure, temperature, and even subtle ground vibrations. Positioned in Elysium Planitia, a region selected for its relatively smooth and stable surface, InSight continuously monitored how Mars' thin atmosphere behaves from hour to hour. Throughout each Martian day or sol, InSight detected gentle rises and falls in air pressure as the atmosphere warmed, expanded, and then contracted again after sunset. Its wind sensors tracked shifting breezes across the plains and recorded the passage of dust devils, revealing how these swirling vortices lift and redistribute fine surface dust. Perhaps most remarkable was InSight's seismometer, which proved sensitive enough to detect pressure waves generated by atmospheric turbulence. Passing dust devils left clear seismic signatures, effectively turning the lander into a combined weather station and ground motion detector. By linking atmospheric and seismic data, scientists gained unprecedented insight into Mars' daily weather rhythms, seasonal variations, and the intimate connection between the planet's surface and its fragile atmosphere, refining our understanding of how Mars remains active today. Mars experiences some of the most dramatic seasonal air pressure changes of any planet in the solar system. These fluctuations are driven primarily by carbon dioxide, which makes up more than 95% of the Martian atmosphere and behaves uniquely as the planet's seasons shift. During winter at one pole, temperatures fall so low that carbon dioxide freezes directly out of the air, forming a seasonal ice cap. As this gas condenses onto the surface, a significant portion of the atmosphere is temporarily removed, causing global air pressure to drop. At the same time, the opposite pole enters spring. Carbon dioxide ice that accumulated during the previous winter begins to sublimate, changing directly from solid back into gas, and returns to the atmosphere. This exchange restores atmospheric mass and raises pressure across the planet. Together, these opposing processes create a rhythmic, planet-wide breathing effect that repeats every Martian year. As pressure rises and falls, atmospheric circulation shifts, driving seasonal winds, influencing dust activity, and affecting the movement of trace water vapor. Landers and orbiters have measured these changes with remarkable precision, revealing pressure variations of more than 20% over a single year, an essential factor in understanding Mars' weather and climate today. Mars is constantly bombarded by high levels of radiation, far greater than anything experienced on Earth. This exposure comes from two major sources: energetic particles from the Sun, known as solar radiation, and cosmic rays, high-energy particles originating from outside our solar system. On Earth, we are shielded by a thick atmosphere and a strong global magnetic field that deflects and absorbs much of this harmful energy. But Mars has neither. Its atmosphere is less than 1% as dense as Earth's, and its once active magnetic field faded billions of years ago, leaving the planet's surface largely unprotected. Measurements from missions like Curiosity and Maven show that radiation on the Martian surface can fluctuate with seasons, dust storms, and solar activity. When the Sun erupts with powerful flares, the radiation intensity at Mars can increase dramatically. This harsh environment affects everything, from the preservation of ancient organic molecules in the soil to the safety of future astronauts. Understanding these radiation levels helps scientists determine how materials weather over time, how deep life would need to exist to survive, and what engineering challenges must be solved before humans can safely explore Mars. High above the Martian surface, thin water ice clouds drift swiftly across the sky, carried by winds far stronger than anything experienced at ground level. Though these clouds are delicate and often barely visible, they cast faint, fast-moving shadows that race silently across the terrain below. Rovers and orbiters have captured these fleeting scenes, revealing long, dark streaks sweeping over dunes, rocky plains, and canyon floors. Because Mars' atmosphere is extremely thin, these shadows appear softer and more diffuse than those on Earth, yet they can move with surprising speed as high-altitude winds shift direction. Their motion provides valuable clues about conditions far above the surface, where direct measurements are limited. In certain seasons, clouds form more readily above massive volcanoes and elevated plateaus, producing extended trains of shadows that stretch for kilometers. Time-lapse imagery shows these patterns flickering and reshaping as clouds evolve, dissipate, or reform within minutes. By studying cloud shadows, scientists gain insight into atmospheric layering, wind strength, humidity, and the subtle but dynamic processes that continue to shape Mars' weather today. Although Mars is a cold and arid planet, small but important amounts of water vapor still circulate through its atmosphere. This trace moisture is released mainly during warmer seasons, when sunlight heats surface ice near the poles and across some mid-latitude regions, causing it to sublimate directly into vapor. Unlike Earth, this process occurs without melting, as liquid water is unstable under Mars' thin atmospheric pressure. Once airborne, water vapor is transported by winds across the planet, rising to higher altitudes during the daytime and settling again as temperatures fall. As the atmosphere cools, this vapor can condense into extremely thin water ice clouds or return to the surface as frost, particularly during the cold Martian night. Over time, this continuous exchange redistributes moisture between the polar ice caps, the atmosphere, and the surface. Orbiters and landers have tracked these subtle movements with precision, revealing a seasonal water cycle driven not by rainfall, but by sublimation, condensation, and atmospheric transport. Understanding this cycle helps scientists trace how water behaves on Mars today and how it may have moved when the planet was warmer and wetter in the distant past. On Mars, even the calmest days are never completely clear. Fine dust particles, some no larger than smoke grains, remain suspended in the thin atmosphere, softening the distant horizon into a pale, diffuse glow. This ever-present haze is one of the most recognizable features of the Martian sky. Because the atmosphere is too weak to settle dust quickly, these tiny particles can linger for days or even weeks, drifting slowly with gentle winds and subtly changing the color and brightness of the horizon. At sunrise and sunset, the effect becomes especially striking. Low-angle sunlight scatters through the suspended dust, creating soft gradients of gold, amber, and muted red that fade into a hazy bluish tint near the sun. Rovers have captured scenes where mountains and mesas appear ghost-like in the distance, their outlines blurred by the fine particles floating between them and the viewer. Studying this haze helps scientists understand how dust is transported across the planet, how it influences surface temperatures, and how even quiet atmospheric conditions contribute to the slow reshaping of Mars' environment. The horizon haze is a constant reminder that the Martian atmosphere, though thin, is always in motion. Mars is famous for its dust, composed of extremely fine, micron-sized grains formed largely from volcanic rock that has been broken down over billions of years by impacts, temperature changes, and wind erosion. These particles are so small and lightweight that even weak Martian winds can lift them from the surface and carry them into the planet's thin atmosphere. Once airborne, dust grains can remain suspended for long periods, drifting slowly across the planet under the influence of large-scale atmospheric circulation. Unlike sand on Earth, Martian dust behaves almost like smoke, spreading evenly and giving the sky its characteristic pale reddish hue. As this dust moves through the atmosphere, it absorbs and scatters sunlight, warming the air while slightly cooling the surface below. This exchange of energy plays a major role in controlling daily temperature swings and shaping regional weather patterns. Over time, dust gradually settles back onto the surface, coating rocks, dunes, landers, solar panels, and entire landscapes in a thin, uniform layer. Repeated cycles of lifting and settling constantly reshape the surface at a subtle scale. By studying how dust grains rise, travel, and resettle, scientists gain crucial insight into wind strength, surface conditions, and the delicate processes that drive Mars' dynamic climate system today. On Mars, dark volcanic sands play a powerful role in shaping how the atmosphere behaves close to the surface. These sands absorb sunlight far more efficiently than the surrounding bright dust and rock, causing them to warm rapidly during the daytime. As the darker ground heats up, it transfers energy to the thin air directly above it, making that air expand and rise in narrow, buoyant columns known as thermals. Even though Mars' atmosphere is less than 1% as dense as Earth's, these thermals can still form with surprising strength. As warm air rises, cooler air flows in to replace it, creating small but persistent pockets of turbulence near the ground. Rovers and orbiters have observed shimmering heat waves rising from dune fields, providing direct evidence of this vertical motion in the lower atmosphere. In some regions, thermals become strongest around midday when surface heating peaks. These rising air columns can help lift fine dust, seed small vortices, and contribute to the formation of dust devils. Over time, they also redistribute grains across dune slopes, subtly reshaping the landscape. By studying thermals over dark sands, scientists gain valuable insight into surface heating, boundary layer weather, and the delicate interactions between Mars' terrain and its thin, dynamic atmosphere. Each Martian winter, a powerful polar vortex forms high above the planet's poles, creating one of the most dramatic atmospheric systems on Mars. As temperatures plunge to extreme lows, carbon dioxide freezes out of the atmosphere and the polar region cools rapidly, causing dense, frigid air to sink and spiral. This rotation, driven by seasonal temperature imbalances and the planet's spin, traps cold air in a swirling, isolated pocket that can stretch hundreds of kilometers across. The vortex acts as a barrier, preventing warmer air from mixing into the polar night and locking in some of the coldest temperatures found anywhere on Mars. Orbiters observing in infrared light reveal the vortex as a rotating structure of chilled gases and thin clouds, shifting shape as it intensifies through the winter season. When spring sunlight returns, the vortex weakens and eventually breaks apart, releasing stored gases back into global circulation. These seasonal changes influence everything from wind patterns to dust movement and even the behavior of the planet's seasonal CO2 caps. Understanding the polar vortex helps scientists track atmospheric flow, model Martian weather, and compare Mars climate dynamics to similar systems on Earth and other planets. Mars is not just a red desert. It is a planet shaped by enormous forces. Its surface holds the largest volcano in the solar system, vast impact basins, and canyon systems that stretch thousands of kilometers across the crust. And above it all, the atmosphere remains thin, unstable, and filled with dust that can rise into storms powerful enough to cover the entire planet. But these extreme landscapes reveal something even more important. Mars has a history, because carved valleys, layered sediments, and mineral-rich plains suggest that water once flowed here. possibly for millions of years. So the real mystery is not what Mars looks like today, but what Mars used to be. In part 2, we'll explore the strongest evidence for ancient rivers, crater lakes, buried glaciers, and subsurface ice, along with the possibility that Mars once held an ocean across its northern lowlands. And if water was once stable on the surface, then one final question remains. Could Mars have supported life?